In this video, we'll look at operational amplifiers and the associated transfer functions. So this is a schematic of an operational amplifier here. And it's essentially got three inputs. It's got what's called V+, which is a non-inverting input, V-, which is called your inverting input, and an output, V out. Because it's an amplifier, it also needs a power supply, so you've got a plus voltage power supply and a negative voltage power supply. And what the op-amp does is the output is the difference in the inputs, it's the difference in the voltages of the input amplified by a large amount, so it's a high gain amplifier. This is a schematic. In terms of its construction, it's constructed from an arrangement of transistors and other components. So it looks fairly complicated, this circuit. I don't want you to worry too much about this circuit. This is just for information. But put the transistors together in this way and you get a very useful component called the operational amplifier. So this is an example of a 741 arrangement. There's lots of different types of op-amps out there. The 741 is your basic bog standard op-amp. What they look like in reality is something like this, where they'll be packaged in a dual inline package. So typically 8 pins, might have more pins, but typically 8. Pin 1, if you look at the top of the device, you've got a little recess there, and sometimes you have a little dot on this corner here, signified by that, and that identifies where pin 1 is. So this is pin 1, pin 2, pin 3, pin 4. And if you look at the data sheet, you can see which pin is associated with which terminal on the op-amp. So in this case, the inverting input is on pin 2, the non-inverting input is on pin 3, and the output is on pin 6. We need to connect power across pins 7 and pin 4. We've got no connection on pin 8, so we don't have to worry about that. This is called the offset null. So on this device, between pin 1 and 5, we've got what's called offset null, and I'll come back to that a little bit later in today's videos. So as I said, this is a very high gain amplifier. So whatever the difference is in the input voltages, the output is a magnification of that difference. The magnification is so high that even a very small difference on the input will saturate the output. The output cannot go any higher or lower than the supply voltage to the op-amp. So if the supply voltage is say 10 volts, so we've got plus 10 volts on that side and minus 10 volts on that side, the output will be limited to between plus and minus 10 volts. So any slight difference on the input, it's going to saturate the output, and therefore the output is going to be typically either plus 10 or minus 10 volts. So in those terms, it's fine as a Boolean operator, so it's either on or off or high or low. But in terms of a useful amplifier, it's got limited applicability. However, to get more use out of them, what we do is put feedback. So we connect the output to the input, and by doing that, we get a lot more ability to control what the amplifier is doing. To work out what the amplifier is doing, we need to use Ohm's law and what's known as the 2 golden rules of op-amps. And the golden rules state this. So it's when configured in negative feedback, so when you have connected the output to the inverting terminal input of the op-amp, then what the op-amp tries to do is it tries to make the input voltage difference 0. So the output will adjust itself, so when it feeds itself back into the inverting input, it'll try and balance itself so the 2 input terminals are the same voltage. And then the second rule is the op-amp draws no current, so there's no current flowing into the op-amp from the inputs. So if we consider them two rules and use Ohm's law, we can work out what the transfer functions are of various op-amp circuits. So let's consider this circuit here. So we've got an op-amp here. We've got the inverting input here, non-inverting input here, and the output here. Now, bear in mind, you do also need a voltage supply on here. So we would have a plus Vs and a minus Vs to supply power to the op-amp. And what we're doing is we've got an input voltage here. And this input voltage is being fed through a resistor into the inverting terminal of the op-amp. So corresponding output V out, and we're connecting the output back through a resistor, resistance 2, back to this input terminal. So as we set in the golden rules, when configured with negative feedback. So we've got our feedback output getting fed back to our negative input. So what we need to do is consider what's happening in this circuit. So there's an explanation what's happening. So what I will do is I will go through this on the diagram. So we're going to have current flowing through here. So we've got a voltage of V in at this point. We've got a current I at this point, and we've got a resistance. Now the voltage at this point, we're not quite sure of, but if we look at the golden rule, when it's connected in negative feedback, the output tries to make the input voltage difference 0. So we can assume the output is changing to make this voltage the same as this voltage. Now we know what this voltage is because this is connected to our earth. So this is 0 volts. And therefore this must be 0 volts as well. So it's not connected to earth, but it's going to be the same as earth. So what we're going to do is call this a virtual earth. So this is virtual earth. It's going to be 0 volts because the op-amp is effectively making that the same potential as earth. So we've got Ohm's law, V equals IR. So I equals the potential drop across the resistor or the resistance. So this current here, I, we'll call it I1. I1 equals the potential drop, which is V in minus this voltage, which is 0, or for R1. Now this current goes here, and it can go either that way and that way. What we said from golden rule 2 is the input draws no current. So we know there's no current goes in this direction. Therefore all the current goes up here. And we call this current I2. And then again this current is the voltage drop across here. So this is 0 volts. The output is V out. So output minus V out. Or for the resistance R2. So we've got I1 equal to this value, I2 equal to that value, and because we know no current goes into the op-amp, all this current I1 goes along here, so I1 equals I2. So we have V in minus 0 or for R1 equals 0 minus V out or for R2. So we've got our two current terms there and there. Them two must equal each other. So we get this expression. If we rearrange that, we get this as our transfer function. The output voltage, or for the input voltage, is the resistor ratio, but it's negated, so it's negative. So this is known as an inverting amplifier arrangement. So the output is amplified by the resistor ratio R2 over R1, and it's inverted as the negative. So in our previous case of the comparator, we said we were getting saturation here, plus or minus 10 volts. Now we've got a very controlled output, so we can amplify to whatever extent we want. If this ratio is 2 to 1, then we're just doubling the voltage of the input. So we can control what amplification we want. So here's an example. Draw a schematic circuit suitable to amplify a voltage from 100 millivolts up to minus 5 volts. So we've got 100 millivolts going in. We want minus 5 volts coming out. So we want a multiplication of minus 50. So we can use this circuit. We need an amplification here of 50. So we have a resistor value of, if we put 50 kilo ohms in there and 1 kilo ohm in there, that gives us our 50 amplification. So therefore this circuit will solve that problem. So I'll just clear my scribblings and start again. Now in principle, we can use any values here we want. So as long as it's a 50 to 1 ratio, so you could say you could use 50 ohms and 1 ohm or 50 mega ohms and 1 mega ohm. So in theory that should work. In practice you are limited to what values you have. We don't want to go too high a value, because if we go to say 50 mega ohms here and here, 1 mega ohm, then the input resistance here is of the order of hundreds of mega ohms. So although that is very high, if this resistance is also very high, you're going to have current flowing through there and there. So the op-amp will sink current. So you have to be careful not to have too high resistance that current does actually flow in this direction. So you don't want this resistance too high. Also, we don't want this resistance too low. So we could say we had 50 ohms there and 1 ohm here. So in principle that should work fine. But in practice, when you make this connection, what you might do is take this wire, take another wire and put a blob of solder on there to make that connection. You haven't done that very good, say, and this has got a resistance of 1 ohm. So this connection's got a resistor of 1 ohm. You've got another 1 ohm here and 50 ohms here. So now you've got a ratio of 50 to 1 plus 1, which is 2. So you've got a 25 gain. Okay, so you need to be careful. You need to use resistances that are high enough that these sort of small resistances don't affect the value, but not too high that you then start worrying about the input impedance of the op-amp. So typically, what you'd have is resistors typically in the range of 1 to 100 kilo ohm. You can go beyond that. You can get away with 100 ohm to 1 mega ohm. You shouldn't have a problem. But typically you want to be worked in 1s to 10s of kilo ohms for resistor values. A similar thing applies to capacitors. If you have a circuit with a capacitance in, then potentially that can be any value. So we can say that might be 1 nanofarad. If you have that too low, 1 picofarad, then what you might have is another line going along here, and you get parasitic capacitance. So because these lines are close together, then you actually get a capacitance between these lines. If I can draw it in. And that might be of the order of a few hundred nanofarads to 1 picofarad. So if you use very low capacitances, again, you have to worry about capacitances in the rest of the circuit just with the lines being close together. So capacitors should also be a relatively large value to get around these potential effects. So when we come to talking about capacitances as well, use tens of picofarads up to nanofarads in your capacitors in your circuit. So that's just a bit of practical advice when you ever come to build these circuits. So we've looked at the inverting amplifier. Here's another arrangement, and this is known as the non-inverting amplifier arrangement. In this case, we put the input voltage on the positive or the non-inverting terminal. We've still got negative feedback because our output is still connected to our inverting terminal, but now we've got a resistor network taking this to ground. So in terms of the transfer function of this, what we have, again, if we work through it, if we look at the potential at this point here, this point we'll call V neg for V negative. We have a current flowing through here, so we'll call this current I, and this is flowing from here through here to ground. We've set no current flows through the op-amp, so that's golden rule 2, so all the current flows from here through to ground. So our current is given by the voltage difference, V out minus 0, which is ground, over our resistance, R1 plus R2. The potential drop across this point is just the resistance times by the current. We know the current is this, so our potential drop across here, so V neg minus 0, so the potential drop here corresponds to our I times by R1, which is V out over R1 plus R2 times by R1. Okay, so the voltage at this point here, corresponds to this voltage here. But from golden rule 1, we set this voltage here, so V on the positive side is equal to V negative, because the op-amp from golden rule 1, the op-amp is trying to make these two voltages the same. So we've got V pos equals V neg, which equals this, and we know V pos is this input voltage V in. So V in equals V out times by this combination of resistors. So if we rearrange that, we have then this. If we rearrange that, we can say V out over V in equals 1 over R2 plus R1. So again, we've got an amplifier. The amplification is slightly different. It's the ratio of R2 over R1 plus 1 in this case. So if we wanted to gain a 50 in this case, we'd have, say, R2 equals 49 kilo ohms and R1 equals 1 kilo ohm, and that will give us a gain of 50. But this is a non-inverting, so if we put in 100 millivolts in this case, we'd then get out plus 5 volts. So it's a non-inverting arrangement on amplifier. This is a special case of the non-inverting amplifier. So again, if I just clean up my diagrams. So if you imagine this circuit here, if we make R2 equal to 0, we essentially just put a wire across here. And if we make R1 equal to infinity, so essentially we're getting rid of this, we have got an arrangement that looks like that, and that's known as a voltage follower. And we've said R2 is 0, so that's 0, that is infinity, and therefore V out over V in equals 1. So this is an amplifier with a gain of 1. Okay, so V in equals V out. Now there doesn't seem to be much point in a circuit like this, but the point is what it does is decouples the output from the input. Okay, so if you have a circuit on this side, you've got a circuit here, and you've got a circuit over here, then you're essentially splitting these circuits up So characteristics of this circuit do not affect characteristics of this circuit. So we'll come back to this a little later on when we talk about filters. But this is a special arrangement for the non-inverting amplifier, and it's essentially it's connecting circuits up but disconnecting the characteristics of each circuit, so one circuit doesn't affect the other circuit. Okay, and that's called a voltage follower. So we'll see an example of that in operation when we come to design some more circuits. So that's the introduction to op-amps, and what we'll go on to in the next video is looking at more operational amplifier circuits.